Hello and welcome back to Calculus 1. This is section 311 and we are talking about related rates. So we know that derivatives measure the rate of change. Change is that division dy over dx, which is a rate. So this means we are going to have multiple derivatives show up in the same equation because related rates is plural, right? So we can still have multiple derivatives in one equation and we relate them through the equation. So we'll see how that goes. Let's start with a simple example. Say you have ice cube. That has a side A. So all sides are A, obviously, because it's a cube. And you leave it in the sunlight somewhere, it's going to start melting. And now, just for the sake of argument, let's imagine that it's melting, right, the same way from all the sides, right? So it will be shrinking and the cube will be becoming smaller, but it will keep the shape of the cube all the time. So I want to know what is the rate of change of volume, right? What is the rate of change of volume if I am able to measure the rate of change of a side? Because it should be clear that as the cube is becoming smaller in size, the side A is getting smaller. And it's not the same if you leave the ice cube in the sunlight or you toss that ice cube in the oven that it's 400 degrees already, right? So the rate of change of side of ice cube in the oven would be much higher than the rate of change when it's left in the sun. So what we are going to do is we are going to establish the connection between these values. I know that the volume equation is V equals A cubed. Now I'll write this in blood in capital letters because this is the key. Change happens in time. So it takes time to see the change. So all derivatives will be taken in respect of time. So as you can see, the ice cube is getting smaller in size, but that happens in time. Therefore, since I am interested in rate of change of volume, I will take the volume equation and differentiate it in respect to time. So what is the derivative of V in respect to t? And the answer is 1 times dv dt. So just dv dt. What is the volume of what is the derivative of a cubed? 3a squared dA dt. Nice. So we took the derivative in respect to time. Volume is changing, so it's a variable. side A is changing, so it's a variable. And when we take the derivative of those, since t and v and t and a are not the same variable, we have to follow with these chains, dv dt and dA dt. Now, sometimes you are going to run into a problem that one of these letter variables will actually be a constant. If you take a cylinder as the example, the radius of the cylinder, r, doesn't change anywhere. So if the radius of this thing is 2 inches, its r is equal to 2 throughout. Where if you have a cone, so think of just this piece of the bottle here, the radius changes. So in this problem, I actually have both shapes on top of each other. So on this part of the problem, r is constant. So when you take derivative of it, it's 0, because there's no change in r. But in this case here, r is not constant. Therefore, when you take derivative of it, it will be whatever it is times dr dt. So here r would die, and here r stays. Yes?
Wouldn't r be a variable for the cylinder if it's melting? So r would be changing then?
That's true, but we have other applications where r will stay, and we'll see how that works. Cool. So we have now this notion, this idea that all of these problems are solved by you carefully reading and figuring out what is that they want to know. Change in area, change in volume, change in side, change in height, and then that is what you are taking the derivative, well, that drives you to write the equation, and then finally, right? So let's talk about, well, what they have in the book is one of the environmental problems, I believe. They have an oil rig, right, which starts leaking oil into the ocean in concentric circles. So as the time passes, the oil spill expands like this. Now oil floats on top, so we just need to go and scoop it up, right? A few square miles, not an issue. Of course it's an issue. So what happens here? When you look at this, we want to know what is the change in area over time. Why do I want to know that? Because the cleanup crew charges by the area they have to clean, right? So I want to know how fast this is spilling, right? And how, well, obviously you just get the cleanup crew as soon as possible, right? But you can project some costs and do things. So, there's a lot of business attached to this particular section. Now, area of the circle. You already know what the formula for that is. What is it? Thank you. So pi r squared. What I need to do is hit that with a change in time. So the left-hand side is this dA dt that we want to compute. The right-hand side, you get 2 pi r dr dt. So if you know what the radius is of the spill and you know how fast it's changing, you can calculate the change in area. So you are going to require some pieces of information to be given to you to find it. But in general, you can figure out, well, and then you can figure out, actually, I can't do two things to save my life. I'm trying to log into the other computer, get to the points in the book. So whatever I wanted to say, just fill in the blanks. Yes. Now, guys, these are your mathematical models. Once you get this, you plug the numbers and you move along. The next part is and something that is very important. You will recognize your values that are given either by words or units. Again, this is in red. Helps you with word problems. Words. If it says change in area in time, well, that better be dA dt, because we know that the change is the derivative, area is capital A, time is lowercase t, and there you go. You put derivative, area, and time all in the same equation, and you get dA dt. So the words will say the change in volume, the change in size, the change in pressure, the change in whatever, change in price. Whatever it is, you are immediately compiling this derivative notation because that's what the change is. And it's always in time. I already put that in red above. So that's one way to recognize either the number that is given or what they are looking for in the problem. The other one is units. If you get feet squared per minute, well, feet squared, what is that? That's area over time, so again, dA dt. I can give you inches cubed, meters cubed. Let's say meters cubed per hour. What's meters cubed per hour? Volume per time, so dV dt. This is how you ace chemistry, general chemistry without thinking. They give you the units, and then you look at the units and you write the equation. If you're not familiar with what I say, general chemistry equations are generally those triplets, and triplets are extremely easy. I'll give you a triplet from physics because this is the one that you're familiar with, which is that distance equals rate times time. Who remembers this? Just the people who don't like to think. Gotcha. Look, what do you know? Every day you have to get here. And that's what? Miles per hour? Is it at miles per hour? There's your speed equation right there. So what's the velocity? What's the speed? It's miles per hour. So if it's miles per hour, so now you go and you apply that to density and moles and everything else. Like this. They give you a unit that has those two things in it. It's awesome. So now we're using the same thing here. If it says millimeters per minute is length per minute, so call it dx dt, dy dt if it's in one of those directions, and so on. So it's quite easy, I would say, to pick up these problems if you learn these aspects. But then we also have whole bunch of formulas for areas and for volume, volume of 3D objects, area of 2D and 3D objects that you guys need to know. So technically, in general, what I find is you know formulas for areas. You know the triangle 1/2 base times height, the square is a squared, a times b for rectangle. So circle pi r squared, right? So we're good with those. It's volumes usually that trips you, and most of the time we deal with volumes. Well, we do have triangles and things like that, but so I will break this up into 3 categories. So 2 categories will take a lot of space and 1 will not. This is what I'm going to do. So category 1, category 2, and category 3. So in category 1, we have our rectangular shapes, like rectangular prism and the cylinder. So we have all of the shapes that are kind of full and boxy, and they look like this, right? So all of these shapes, have a base and height. And the volume is always base, area of the base times height. So that base could be square, could be rectangle, could be triangle, could be circle. So all of that stuff, it doesn't matter what it is. We call these prisms. So you have a rectangular prism, triangular prism. It doesn't matter. So it depends on the shape of the base, but all of the areas are this. Then we have what I call spiky objects, which would be a cone, like a witch's hat, all right? I would talk about ice cream cone, but then Brian only had a kiwi for breakfast, so I'll try to avoid food references until you guys decide not to have the exam when he needs it, and then I can eat 20 brownies. Awesome. Well, actually, no, you technically don't count, so you can eat brownies too, no matter the outcome. So
only people that are neutral and in my favor get brownies.
Yeah, I'm neutral.
No, you weren't the last time we voted.
No,
see?
I'm in favor for brownies. That's all I care.
Yeah, right.
I was not here last week.
When the test is.
Oh, is that why the class went well?
Oh.
Yes. Right.
All types of pyramids also fall in the category of spiky objects. I can have a square in a base, like pyramids in, well, actually, pyramids in Egypt are actually 8-sided.
What?
Yeah.
Was it smooth on the corners? That's what you said?
No, it's actually these over here, there's a very, very tiny spiky piece.
Base, you mean?
Yeah, in a base. So it's 8 football field size, right? You can only see them during the equinox, actually. There is a little bit of a shape. Yeah, it's interesting, but you know, for purposes, it's just 4. Okay, let's go with 4.
If you want to be technical, they don't have they have a bunch of other sizes that go like this constantly. You have to do that now.
Aliens made it.
Why am I here instead of reading humans, dude?
Okay, I will have to actually pause the stream and talk about pyramids for like an hour. All right, I'm serious about that. So yeah, let's not. And I'm going to go with aliens, sure, because I don't know how they stack 2.2 million half-a-ton blocks perfectly on top of each other without a crane, a pulley, or anything like that at that time. From the quarry that was what, 300. It's like in Washington, D.C., all right?
There's actually a pretty good logic behind it.
Impressive.
Limestone underwater actually can float if you separate it. So the theory is that they brought it up like that, carved it in the water, and then floated it to the location, and then put it up and stacked it.
Awesome.
The other theory is they wet sand underneath it, which makes it actually slide, which is weird.
Yeah, I would love to see you slide 500.
Well, no, you just or you can go with the classic solution where you start human pain and suffering at it until it works.
I know, Paul. The other brilliant idea was that they, roll them on trees, like on,
Yeah, that would work.
It's a desert. Where do you get the trees? Right? Yeah, the pyramids.
Yeah, we were pretty rich at the time, relatively. And stuff.
Yeah, I know. It's still a desert. Okay, and the stuff, and that sinks in sand. So. And the copper tools don't cut stone. That's another thing. And yeah. Anyway. So aliens, right?
Yeah.
They went live.
Apparently the people that built these pyramids were not slaves, they were actually paid laborers.
Yeah.
Yeah, but paid like
With whip.
Well, it's either death or prison, right? So
Yeah,
it's.
I don't think there was whips. I think it was more the fact that, like, I don't know, when you're lifting huge blocks, it doesn't really matter how many people you throw at it, you have to at least have some idea how to move it.
Anti-gravity gun from Half-Life 2.
From space.
Does the job.
They're never gonna make it.
Yeah, I was just thinking that.
Oh, my gamers now are like, yes, he said it.
They're too busy making too much money from Steam. They don't have time to make games.
Feels bad now.
So, guys, when you put these in categories, you have non-spiky objects on one pile. It's just area of the base times the height of the object. Then you have the spiky objects, which is 1/3 area of the base times the height. So the difference between the cylinder and the and the cone is just going to be in that 1/3. That's all. And in the third category, on its own, the one and only, very special sphere.
Boom.
Good morning. I spent the entire summer drawing these. Yeah, practicing drawing circles, and look, now they're perfect. Hold on, sphere is when you do this.
Ooh, there we go. Could you make it a globe instead? Like, draw comments on it?
No. Which has its own formula, 4/3 pi r cubed. And that is the perfect shape. So we have these three categories for all volumes that you can run into. Other volumes will be composed from these, so you would cut. So as I said, if you take this and you call this a cone, so you would cut here, you have a cylinder, you have a cone. And then you do them separately. So you should know all the areas. Now you've seen all of the volume formulas. Every time you see the B stands for a base. Base is the area of the base, which is one of the 2D concepts. And once you have that, you are able to work on any of these problems. So now, let's take a look at some problems. We already saw two problems. One is the melting ice cube, and we developed the formula that governs how fast the volume of the ice cube changes in terms of the area. Now, guys, volume, that would be inches cubed per minute, per hour, per whatever, which can be transformed into the volume of the runoff water. So you can actually do this. Math Club in 2010 or 11. So Math Club went into the chemistry lab and took some of these, took ice cubes. You measure the ice cube, and then you measure how much water goes off. And we plotted these things, and it was amazing, amazing fit. And you can relate the water, and you are going to have on your project, which will be posted over the break. One of the project questions will be dealing with this. Savior.
Can you see the stairs?
Yeah. Savior prayer. God is not here with us now.
There's no God here.
Do what? Yeah. Here comes the planner. This is going to plan your next 2 months. Brian will fill in the details.
I still have scars from it.
No, it's not. It's only 4 problems. What are you talking about?
Yeah.
Just do it the final exam. You have 2 months for 4 problems. Come on.
What exactly is
The final product,
We'll talk about it later.
how much is it?
What happened? What happened?
How much is it?
It's 10%. Yeah. It's not, I mean, 10% for like a 12-page paper is not a big deal.
sounds good, like, yeah.
Or that's what you think.
Yeah. Maybe more. Mine was immaculate. Holy shit. And then I bombed my non-final because all that time during the project. But that project.
Awesome, right? I spent a long time to figure out those problems.
And then in
you spent even longer to
too,
solve
it
it.
was the first project, and I did it how you do it, right? And like the professor was like, "What is this?"
Sad, right?
Yeah.
Okay, let's take a look at some of the problems that are available to us in the textbook. I'm not going to redo problems that are done in the textbook because you know all the letters and you can read that stuff. Or I could, if you need clarification. So, problem number 8 says shrinking isosceles right triangle. So I'm going to draw a triangle that it's 3 squares each side and then connect. I have the y direction, x direction, and let's call this one b. We could have called it hypotenuse h, but I don't want to get confused with height. So it's just distance d. The hypotenuse of an isosceles triangle decreases in length at the rate 4 meters per second. How do I write that in mathematical terms using this d? Negative 4, excellent. So equals negative 4, but what do I put on the left? d dt. So the lowercase d is for that distance, so we can call it length. You want to change it into L, we can. You want to do the L? Okay, so here. This is just for you who use pens. So your notes can look disgusting now.
I've crossed so much shit through this class.
You bought a erasable pen just for me. Oh yes, I am honored.
I used to get fountain pen. I don't think that's erasable.
All right, so here we change that distance to L. So the length of hypotenuse is L. Now here, I want to read one more time. The length of a hypotenuse of an isosceles right triangle decreases at the rate of 4 meters per second. So that's what we have. dl dt is equal to negative 4. Yes?
This is y and x equal to each other?
Yes, isosceles triangle.
So
Just as. At what rate the area is changing when the legs are 5 meters long? At what rate is the area changing? Look how I write that. At what rate? That's this peanut. At what rate? And then is area changing? When the length of the side of the leg is 5 meters long. So now we know the area of the triangle. Hopefully, what is it?
1/2
Area of the triangle is 1/2 base times the height. Now, in terms of our letters there, x squared, very good. So 1/2 x squared in terms of our letters from the picture. Because y is the same as x, we can just keep x all around. And I hope that you just see the half of the square, guys. You see a diagonal cut square? Well, clearly has to be x squared divided by 2, right? Awesome. So we have that. Now, I have an equation which I can take the derivative of in time to find the rates of change in time. So I get dA dt equals to 1/2 times 2x dx dt. Then this 2 dies, right? Like that. And we have dA dt is equal to x dx dt. This is called the mathematical model. That's the math model for this problem. Now you keep giving me different numbers. I will give you different answers, obviously, because now look what you have. The length of this length is changing at -4 meters per second, and x is equal in meters. Okay, cool. But hold on. I have dx dt. What's given to me is dl dt. So if I am to go through a problem and make a check-off list, I check off what I'm looking for because that's unknown anyway. Dx is given to me, x is given to me, so that's okay. But I need this part, right? So I need to figure out somehow this dx dt. So how do I figure out dx dt? Nice. Pythagorean theorem. So we have that 2x squared is equal to L squared. From where L is equal to root 2x. If you square root both sides, you will have plus and minus, but lengths are never negative. Therefore, we just keep a positive root 2x. And now I differentiate that to establish the connection between the L dt and dx dt. So from there, I see that dL dt is equal to root 2 dx dt. Now I know that this is -4, right? dL dt is -4, so I have -4 is equal to root 2 dx dt, from where dx dt is equal to -4 over root 2. Then we rationalize that. Times root 2, so -2 root 2. Now I can plug everything in. dA dt, what I'm looking for, is equal to x, they said that's 5, times -2 square root of 2, which is -10 root 2. Meters squared per second. That's the answer. This is an interesting problem. So we start with isosceles triangle, right triangle, which is actually half of a square cut diagonally. The problem says the hypotenuse of an isosceles right triangle decreases in length at the rate. So hypotenuse decreases in length, that's dL dt for the hypotenuse, and that's -4. At what rate is the area of the triangle changing? So if we have a negative change on the length, that means that the whole triangle is getting smaller, so you better get negative change in area because the area is getting smaller. That should be common sense. So we start with dL dt is equal to -4. We write down what we are looking for, which is dA dt. and the information they gave us that the side is 5 meters long. We write the formula for area. It's always the same steps. We write the formula for area. We differentiate that area in respect to time to find the change in time. The mathematical model we get is also known as related rates. So you have 1, 2, so rates, plural, right? And it's related through the formula of some sort. So we got our related rates math model. And then we check off what we have. So dA dt, I'm checking that off as I have it because that's what I'm looking for. X is given, it's 5. I don't have dx dt. So I have dl dt. So if I could relate dl dt to dx dt, I can figure out what dx dt is. So we use Pythagorean theorem, as Eli said. We use Pythagorean theorem, so x squared plus x squared is equal to L squared. So 2x squared equals L squared. And then we grind through math. We take the derivative in respect to time to relate change in hypotenuse to change in one of the legs. Once we figure out change in one of the legs as negative 2 root 2, we'll plug that here, we'll plug a 5 there, and we will get negative 10 root 2. Meters squared per second. That's 1 point. Units, correct unit. Now, in your textbook, this was this particular problem was given regarding 2 airplanes on a collision course, right? So as the 2 airplanes go on a collision course, one airplane is going this way, the other airplane is going that way. And they're on a collision course, they're on the same height. The distance L is the separation between the 2 planes. You see that that distance L over here is 0 because look, as the planes, both planes get closer, this L is smaller. You see that how it's changing? That's what the change is, and that happens in time because it takes time, airplane, to go from point A to point B. So this question is explained in textbook through the airplane, and now what I did is I did the vanilla example in the, in general terms. Guys, this is actually highly applicable. And by the way, I found out in recent, actually 2 months, from 2 different sources that we're going to have a shortage of pilots and air control and all of that stuff. So that might be a field that you might want to look into.
Can I ask why? Because just no one wanted to do it.
A ridiculous quantity of training due to the fact that many people do it as a labor of love, about the fact that a lot of pilots being laid off or having their wages reduced over the past 10, 20 years.
That was amazing.
Yeah.
My grandpa was a pilot.
Professor, do you
yeah.
think it'd be valid to teach math as like a story? Like, okay, so here's like the planes crashing into each other. Now calculate, the shrapnel and like the people being ejected from the plane.
Yeah.
What?
Yeah. That's the map of the airspace above United States.
Yeah, that seems valid.
You gotta make sense out of this mess. You gotta track this. Computers will always do that. Here's New York and Newark and LaGuardia, or the airports that are major, are right there. There's the Philadelphia one. So, yeah.
Wait, what's the West Coast look like?
Like pandemic.
West Coast?
Never expect that again.
Not a problem. As you can see, not a problem. Like there's not that much activity in North Dakota. We have 7 airplanes, all right? It's a natural preserve. You don't want to scare the moose, all right?
The Midwest doesn't exist. It's
But
like the East Coast.
but
and
you
the
have
West
to
Coast and then
you have to manage this mess. Obviously, you would use something like there's a bunch of software that does these things, but yeah, where the penguins are.
Yeah.
So here we come up, coming up Europe.
Wow.
So we're coming up Europe, and you gotta manage this. Now each of these airplanes, this is all live. This is a live map. So if you ever have anyone fly or you fly, you can follow these planes. Each single one you can click on. They will tell you exactly which plane it is. You have it where it is, the length, where it's going, how fast, and
I don't want to touch that right.
You get a picture of it too.
there's the 3D view.
Ooh.
Let me see.
Wait, what? You can get a.
Yeah.
You can get a friends and. Ooh.
Uh-huh.
I'm guessing it's
What?
Google
It's not dangerous. Like that's not.
No, it's not a cameraman standing on a plane. Don't worry about it.
No, I mean, like, it's not. I mean, we have like all these satellites. We might as well use them, right?
Yeah, just overlay that over Google Earth.
Like,
It's
if
fine.
somebody's willing to bomb a plane or do something horrific like that, we'll take them
Guys,
out with it. Not much
if you know where the thing is, 10,000 miles. Don't worry about it.
That's what FATs are for.
That's what air marshals are for. There's air marshals on most U.S. flights.
All right. So you get the idea of what kind of stuff as the air traffic controller you deal with, and what we did there was related rates for 2 airplanes. Okay, over here we have a couple of thousand. So computer science. Anyone? You can write a software to follow this. All right, integrating what we did here on thousands of planes between locations and so on. They have to have their heights, their speeds, their landing patterns, and all of that stuff. It was negative 10 root 2.
10 times square root of 2.
Wasn't there something that, oh, okay, yeah, figured.
Meters squared per second, again, because it's area divided by time, length squared divided by time, so square. Awesome. So now we have that, and that was great. I love it. Let's see what else we can do.
Let's realize all that plane example is also in the stream.
Yeah. Stream did not catch any of the website stuff.
They're just very low.
So here I'll give them the URL of what I showed. So www.flightradar24.
See, this is where you like more than just math. Real life.
Really, like Switzerland is like impossible to invade.
Yeah, they have bombs at all the mountain passes and bridges. They can instantly make like a metaphorical island out of themselves.
And every
So let's
single
just bomb
person,
them from orbit.
every single person is trained in the military.
Yes, because everybody has mandatory military service.
And they all have.
And what? And that little utility knife with the wine opener? They just get everyone drunk and that's it.
Like all they have to do is get into the
Awesome.
farm is go get ammunition.
I'm surprised the U.S. doesn't have. I mean, we have the mandatory draft, but like.
All right, let's.
The U.S. is impossible to invade because there's
Shrinking
a ridiculous
circle,
fucking gun
expanding
series. It's
cube.
trying to invade, like every other bush would have somebody with a gun willing to just like spray and pray at them.
Melting snowball.
Yeah, melting snowball.
Snowball, depending on how OCD you are, should be a perfect sphere. And it says a spherical snowball melts at the rate proportional to its surface area. Nice. Show that the rate of change of radius is constant. This has honors like spelled all over it. But it's awesome because we get to review all of the formulas for sphere. So we do it. One more time. A spherical snowball melts at the rate proportional to its surface area. So this is what we write. The volume in time is equal to k dA dt. This is how you say that two things are proportional. You equal them through a constant k, because that's proportional growth. So this statement says that the spherical snowball melts at the rate proportional to its surface area. So the loss of volume is proportional to the loss of surface area. show that the change of radius is constant. All right, so now, what do we know from these things? Well, first of all, we know the volume equation, which is 4/3 pi r cubed. And this being the perfect object, if you take the derivative in respect to r, you will get that the area is 4 pi r squared. This happens only for circle and sphere. Those are the perfect objects. So for circle, if you are to take the derivative, so area of the circle is pi r squared. If you take the derivative in respect to r, you get that the circumference is 2 pi r, right? 2r. That only happens for circle and for sphere. It doesn't happen for anything else. You can try square. What's the area for the square? X squared. What's the perimeter for the square, which is circumference? What's the perimeter? 4x, right? Not 2x. So you see, it doesn't work. So this derivative thing works only for sphere and for circle because they're perfect objects. So you're memorizing the volume formula for the sphere, and you're realizing that the area is just the derivative in respect to r, if you want, or you can just memorize the formula as well. So these are the two formulas. All you need to do, hopefully it's clear, all you need to do is to take those two derivatives and plug them in up there. So what's dv dt? It is 4 pi r squared dr dt. And dA dt is very good.
Okay, we were thinking that.
I know. The what? Oh, okay. Listen. So now plug in, and we have that dv, so it's 4 pi r squared dr dt is equal to 8k, so 8k pi r dr dt. Divide both sides by r dr dt. 4 pi, we can divide both sides by 4 pi r dr dt. 4 pi r dr dt. So that dies, that dies, that dies, that dies, leaving only r. On the other side, that gives me 2k, and then r dies, the r dt dies. Awesome. Look what we get. We get that r is 2k.
Well, we can find out what the
They say show that the rate of change of radius is constant. Well, what do we see here? Constant, right? The other way you can do this is you can solve for, like, move all of this stuff to the other side. So other way would be to, should I say way 2? I don't know. Move both of these to the same side. So 8k pi r dr dt minus 4 pi r squared dr dt equals 0. And now factor dr dt. and you have 8k pi r minus 4 pi r squared equals 0, and you see that this is not 0, so this one is, which means constant radius. So a little bit of the interesting problem. Let's see. Ooh, the sand pile. Yes. All right. Engineering. There we go. So I have a conveyor belt.
Engineering, aka people will actually get hired in from.
I refuse that.
I'm not, no comment.
The sand is coming on the conical pile over here. And then what happens is, as more and more sand comes in, the sand pile grows. You can see that the radius r is growing and the height h is growing as well. So we want to know how to design, let's say, a shutoff switch. If this is a query, there's a lot of dust. You can't really use those photocells to say, okay, the pile is this tall, and then just cut it off, because that's all that photocell is going to get dust all over it, and it's just going to be off all the time. All right. So maybe some kind of timer switch or something that again, it's going to be, yeah, but it's all related on how much sand it's coming in over time. So again, related rates, right? Because that's related to the volume and so on. So the incoming sand here is clearly dV dt, which is change of volume of the cone, because all of the sand coming off of the conveyor belt falls on the pile. So volume-wise, whatever was on the conveyor belt is the extra volume that it's being added to the sand pile. I want to know how fast is that volume changing, because that is going to give me, how much volume there is eventually. Now, this is one of the craziest problems, because there's a lot of stuff going on here. We all see the cone. What's the big deal, right? Well, it's a big deal because you actually have two independent variables that grow, height and radius, right? So as I write my formula for volume of the cone, we know it's a 1/3, and then area of the base, right? BH is a spiky object. So area of the base, that's a circle, that's pi r squared, and then times the height of the cone. Now, do you see what's changing here? Radius is changing, height is changing, therefore they're both variables. So when I take the derivative, what do I have to do?
Take the derivative of those and solve them.
Yeah, but what is the proper derivative I'm taking here? They're both variables.
Oh, so product.
Product rule. R is multiplied into H. It's the product rule.
Oh, that's easy.
So dV dt is equal to pi over 3 is a constant. And now, copy the first, derivative of the second, plus copy the second, derivative of the first. Do we all see the product rule at large? Now, I'll just put as a side note here. If this was a cylinder, if sand is to fall onto a cylinder, which you can have actually, because you can have a silo and you put the corn into it from top. Silo is a cylinder. this equation would not look like this, because the radius is constant, in which case for the derivative you would copy pi r squared, you would copy that and you would just have dh dt, because as you put the corn here, the only thing that's changing is the height. Radius doesn't change. But as you put the pile on the sand on the pile, it creates a cone. Radius changes because it gets wider, and the height changes as well. So you have both of those to be variables, which when you put that together in a formula, you see it's a product rule, right? Because they're both variables that change. So this is my mathematical model known as related rates, right? So I have mathematical model. So I need all of this stuff. So what is the trick for this problem? The trick is that you don't have the h dt and the r dt given to you. Usually radius is easy to measure, right, because it's on the ground. But what are you going to do when the sand pile is 11 feet tall, right? And keep adding. We're talking big quarry, right?
You can find out the height, you can find out the radius.
That's true, but it's all of that stuff is changing. I wanna measure the change. I can measure the change easily, because I can just I can have on the wall this kind of thing, right? And then the sand is falling like this, and it's kind of creeping up and creeping up and creeping up. And I say this is 1 foot. So I just time 5 minutes for 1 foot. And there it is, right? So it took me 5 minutes for 1 foot, and I have the RDT, right? So it's easy. Now for height, it's not easy to do something like that, because you would have to be far away. You have to be in the eye level of the thing, right? So the height, the HDT would not be cool. So usually you have the RDT, you do not have the HDT. Yes?
Can you put a big stick in the pile and like have the measurements of the stick?
Yeah, so it's pretty inefficient though.
I mean, we're saying
Yeah,
like, really
because
ghetto ways to do this, right?
yeah, but see, the thing is that the stick would actually have to always remain sticking out the top. But what you're gonna do if the peak kind of forms right there, right? But then well, look, you're standing here, and when you're reading like this, look at the error. Height is almost impossible to measure in these kind of things, unless you are in the eye level. But we are talking that level changing from 6 feet where you are in eye level. Well, you are in eye level, right? For some, it's like 5. All the way up to 11, 12, 30 feet.
You can cast a shadow for a big ass light, and then maybe how long the shadow.
Which again, the light has to be there. You don't want to have the sunlight and all of that kind of stuff. There's a lot of dust. It's just bad. So easy stuff to measure, the RDT. And now what do we do? Similar triangle, and we do the same trick we did over here to relate those guys. So I'm going to say that if I look at the triangle, this is the height of the pile, this is the radius of the pile, right? And then we're going to have the second state. Yeah. When this is larger. Call it capital H and capital R. Where these sides are parallel, right? So now H is to R what H is to R. That's a constant. So you can see that the height is equal to HR, which is a constant, times little r, and then you take the derivative of that, and you have the related rates to plug in to replace the bad one right here. Then you plug the rest. So these kind of problems, the book has the example. I'm going to show the book right now. This problem is solved in a textbook. I just wanted to talk about it so there are no issues when you read it. So here is the pile of the sand. They're dropping it. It's not a conveyor belt. Doesn't matter. Yeah, you can play with that if you have it. Oh, they did it differently because a sand falls on an overhead accumulating conical pile with the radius that is always 3 times its height. You know that capital R and capital H? There it is. So that's that information, 3 times its height. So now you have there, depending which way you put, you either have 1 over 3 or 3 over 1. So you have that piece, and then you just plug the rest in the equation, and it actually simplifies these equations, and then you get the number at the end. So that's that part. We have this. All right. One more problem for related rates, and then we're going to take the break. We'll talk about the date for the exam. Some of us are going to eat brownies, or all of us are going to eat brownies, depending on the vote. And we'll see. So let's take a look at one more problem. And that one more problem, again, is something that you guys might consider as your career. So for that, I want to find the video. And you know what? Since I kind of feel bad that the stream didn't get to see it and didn't get to be captured. So let's go like this. Okay. That one is 3 hours. We don't have time for 3 hours. Maybe this one?
Oh, we have 3 hours in this class. Movie night, right?
Gladiator.
Maybe that's a good one.
So we see well, you don't see yet. Now you see. Oh, see what you guys see and what they see. All right, so we see the rocket on the launch pad.
Release resupply services mission. This is the first time a launch vehicle has left Earth from 39A since the Space Shuttle Atlantis in 2011. Everything continues to proceed nominally. We are just about to transition through Max Q, maximum aerodynamic pressure.
You have a guy standing like 3 feet away with a cell phone.
Stuff just duct taped into a stick.
Max Q is one of the highest stress states on the rocket.
I just need to find a good video.
Good one.
I should.
We should go there ourselves and just get one for further.
It's the next math club project to go and actually tape one of these, which is actually why you guys are all here now. All right, so this is a good video. It's not routing sound, but we don't need the sound. Launch happens pretty soon. So you see that the camera is showing the rocket in the shot. There it is. And now look how bad this is. The camera didn't move. The rocket is gone. Oh, but now look, the rocket is actually in the middle of the shot, which means that the camera is moving. But look, the camera is moving faster than the rocket, right? So, wow, right? Not that. This is actually what I want to see. This is exactly what I want, to show an awful situation for the, you know.
This is what not to do.
Yes. Now, so SpaceX, in all of its infinite wisdom, in making the rockets that are reusable, that land back on a floating raft in the ocean, right? They're able to figure all of that out. They're not able to figure out much simpler problems than how to record it, right? So let's help them using our problem. I'm going to create a problem out of this. Something similar is done in a book, but on not as cool of a concept. So let's just make it cool. So here it is. Then you apply to SpaceX with this stuff, right? Apply it to their needs. So here we have Mother Earth, and we have a rocket. Now also my rockets are far better, as you can see. Look at that. Looks like a missile. Now this thing is going to shoot up the height at dH/dt, which is the speed of the rocket going vertically up, right, to achieve the escape velocity. And over here somewhere, I'm going to put the camera. Look at my camera. That's the next. My camera. That's the next next millennium stuff. And we are going to put this camera at the safe distance L. Okay, so that's a safe distance. So it's not getting knocked off. It's not getting rocked by the launch, and it's definitely not held by a human. With what's the name of the?
What's it called?
Parkinson's.
Yeah.
So I know it's terrible, but you're sitting in calculus, so deal with it. Somehow I knew that you will know. Now look, what do I want? I want the camera has the view of the rocket. We actually had that in that video for a split second when the rocket was in a shot, right? And then the camera kind of went woo, and the rocket was no longer in a shot. So we are thinking the average, right? This is a straight line. And then what's happening here is there has to be some angular velocity omega that this camera is going to take as the rocket is going up. The camera will be simply raising to keep that rocket always in a shot. It's a related rate problem because the angular velocity omega is this change in angle theta. So if you studied physics before, you know that you have linear velocity and acceleration, which is good old v and a, and right, and then you have the same world, right, transferred into angle theta, and then the change in theta in time is omega, and then alpha, which is angular acceleration, and so on. So now I have all of the ingredients to actually build this easy. If you look at this, tangent theta is equal to opposite over adjacent, so height over L. L is a constant. It's a safe distance. 500 feet, 1,000 feet, right? So you put the camera at the finite. I could put the number there, but we want that to be the minimum safe way. So, and I don't know what it is, so I'm just going to keep it as L. So now what's happening? I want to find the change in theta, which is angular velocity, at which we need to program the servo Servo is a motor that slowly raises the camera to move the shot so that rocket is always in the middle of the shot. So I find the derivative of this in respect to time, and I know that the height is changing and the theta is changing because I want to change that angle so that rocket is always there. L is not changing. L is constant. I'll write that one more time. Constant, variable, variable. So what do I have? When I take the derivative, what's the derivative of tangent?
Oh,
Very good.
yeah.
And then we follow with d theta dt because theta and t, right, not the same variable, equals to, on the other side, I have 1 over L constant. You copy that, and derivative of h is dh dt. You can see, and that should make sense, that the change in angle depends on actually angle and speed of the rocket. Those are the two variables that would tell you how fast you have to change the angle. Does that make sense? Well, yes, because the angle has to change more rapidly here and then less rapidly there, right? Because the rocket, if the rocket is going to go, let's say it's going at a constant speed at all times, right? For this half of the trip, the camera will have to move faster because over here, rocket is further away, so it moves slower, right? You know how when it's easiest to hijack the plane, right? When it's all the way up in the air because it's small.
Oh,
I think that's the stupidest joke I've heard this year.
I know. I heard that last year from one of the students said that it was Calculus1, I guess.
I don't think anybody's going to top that this year.
Yeah, I don't think. Yeah.
Try. Like,
Yeah,
don't
you know, it's like, but when you look up, right, the airplane's like this big. It's like it's nothing. It's easy. All right, so now we solve this for change in theta, which is what we need. So d theta dt is equal to 1 over L, 1 over secant squared theta, dh dt, and a shiny quarter to one who tells me what 1 over secant squared is. Exactly.
Of course.
And engineering problem solved. Guys, I want you to understand that this is your job as engineer, right here. This. You have to be able, if you want to have that engineering job, to pull this off. Here's the problem. This is what I want to do. What are the concepts that go together for this? You come up with this equation, and now you say, do I have the data for the speed of the rocket? Yes, I do. That's something we can put in the code. Do I have the angles? Yes, because you can measure the angle, and you will constantly update the software, right? So you will, again, write the code now, and you program all of that into, I don't know, you know, whatever it is you use, and you will have a perfect shot for the rocket going in. So this kind of videos, right, would not happen where you have this kind of shot. Well, oh, this is a good shot. This is action shot, I guess. That's
All the engineers were building the rocket ship and they got that intern to shoot the video.
right, it was literally someone standing there with cell phones. Like, it was terrible. Like, all this hard work and all this engineering and all these brilliant people making amazing things, and look at this shot. Like, what is this? I don't know. Yeah, look at that. Right? Then they moved to a tripod, 3 hours later, because they figured out that the initial shot was done. Or no, they brought the rocket back and they just launched it again, so they have a good shot now.
I mean, that's the point of reusable rockets, right?
Yeah.
I also use those ones. What year do you think will colonize Mars? Never.
Well, so problem is solved. Again, you would code something like this. If the safe distance is 1,000 feet or 700 feet away from the launch pad, that number goes there. You leave theta as a variable, which you have the initial theta. Theta 0 is 0 degrees, right? When it's flat, it's kind of shooting directly at the rocket. And then as soon as it starts moving, the theta will be changing. You are reading that theta as it starts going up. You're reading that theta and feeding it constantly back in the equation. And you update the equation. The update cycle depends on software and hardware you have. The DHDT is updated from the speed which is known from the rocket. That can be computed as well. Fit everything in one equation. Put it in a code. Feed it to the controller, which will drive the servo, and servo will perfectly put the camera up and take the shot.
That's too expensive to test.
No, it's not. It's just someone needs to care. But I just gave you the gateway to apply for SpaceX, so go ahead. That takes care of the related rates. There is a whole bunch of problems. When you open the book, every problem will look different, but then you talk to me and I tell you every problem looks the same because every problem has the same steps. Step number 1, understand the problem, collect the information. Step number 2, write the geometry of the problem, which is formula, and take derivative in respect to time. Step number 3, plug the numbers in and profit. So every problem is the same instead of steps, but if you are used to that, I need to see every type of the problem before I can do the problem, and well, then every problem is different, and you won't see every problem because it's impossible. We have 60 different problems in that respect, but the core is the same. You always follow the same thing. You see they ask for change in area in time, that's dA dt, which means because they're looking for dA dt, write the area equation, take derivative in time. You must have at least 2 related rates, right? So dA dt and the, x dt, say. But you saw in the conical pile problem that we had 3, and you can have more. So in that case, you will have to look for other connections so that you can take those derivatives and connect them all together. What happened to my wall? All right, so that takes care of this section, and that takes care of the chapter. Now let's discuss the date for the test. And
yes.